what is a computer as such? It is actually a programmable machine. So this device is a programmable device which receives certain inputs. It stores the input if required and manipulates the data. Then it provides an output in a useful format. So data will have to be acquired, data will have to be processed as per a stored set of instructions. So we have the tool now. The tool we make use is the computer system itself. It will have its own gadgets. It will have a memory also. Now, how the problem will be expressed? The problem will be expressed as a program in computer science. There are different ways of expressing a problem in different fields of study. Okay, you can take it in mathematics, for example, how a problem is expressed there. Similarly, in computer science, we have programs for that. Solutions are written as programs. What is a program then? To a specific topic. So there are occasions where we'll have to recap everything. Now, what is a program then? A program is a sequence of instructions. And most importantly, these instructions are to be executed by a machine to solve a specific task or a problem. Now, when we say that the job is to be executed by the computer, there has to be some kind of mechanisms for that. For such cases, a programming language is being developed. Now, we have seen that this is also the job of a computer scientist to develop both the hardware and software tools that will assist a programmer to solve a problem. So now a programming language is a language itself, which is designed to express the solution to a problem. So we make use of C to express our solution. We have the solution blueprint. Once the solution is clear-cut, we can use any language for that. Ultimately, whatever may the programming language we use, all these will be translated to machine language, whatever might be the type of programming language that we use. How a problem can be solved now, especially in computer science. Since computer science is all about problem solving, since computer is a machine designed to solve problems, and there are even representation of a problem is as a program, now we should know how the problem can be solved in some fundamental steps. See, the first thing is defining a problem, how to do a task. Directly, you cannot rush to a machine and start coding. That will land you in trouble. You should not be in a haste to start coding. Before you code, you should know what is to be done. I discussed this with a simple example earlier, like say adding two numbers. You will have to ask questions to the person who asked you. It can be your customer. What kind of addition you would like to make? And then based on these questions, you will know what are the inputs required. What's the output required? Should I store the output somewhere? Can I reuse the inputs? Or will the inputs will be also received on the fly? If it is to be stored, how it can be stored? Is it on a temporary basis? Is it for the current iteration? Is it for the next execution, possibly tomorrow or after 1 year? So all these factors, different factors will have to be taken care. And based on that, we will arrive at the definition of a problem. Once the problem is clear cut, then we will, from there, we will enumerate the inputs and outputs required. Input is the data that we receive. Then we have a black box called as a program. It will produce some output. In between the process comes. Then we will formulate a model. Oh, what's a model you formulate, say, for addition? It's a simple equation. Say if you have A and B, you will say X equal to A plus B. That's a mathematical model you make for adding two numbers. And we will say that A and B can be either whole numbers or real numbers depending upon the case. We also say that A and B can be signed numbers or unsigned numbers depending upon the requirement. Once a model is specified, now we have the steps. We will describe the steps for arriving at the solution. And these steps are called as algorithms. Once the steps are described, we will check the correctness and efficiency of these steps. See, still we haven't done that. The programming language has not come into limelight so far. The algorithm is to be tested. We'll say hand execution. We will hand execute the algorithm as the way a computer does that. We know how to calculate 2 plus 3 and we'll say 5 in a single step. But when the task is sent to a machine, it will be, the entire task will have to be subdivided into a sequence of instructions. First might be how to receive these values. So this depends upon the requirement. Do you require a program for demonstration of addition, assuming the values by the programmer? Or do you want to receive the values from the user always? That's the first question. Do you want any kind of validation checks? What will happen? What should I say if user key in, say, 3A4 instead of 3? Should I give a chance for the program user to correct his input, or should I abruptly end with a cryptic answer? So all these things we will check with the customer in which way he requires the solutions, and based on that we will articulate these steps. Once these steps are written neatly, we will hand execute them. We will obey all these instructions on our own. Then we'll see that once a correct set of input are provided, it will produce the intended output. If that is made sure, then we will implement these steps. This implementation is called as development of program or coding. Once the coding process is over, still we will test it once again. We will test and evaluate the results. Then our product is ready for delivery. After the implementation, the program will be tested once again and the final product will be delivered to the customer. Now, these are the fundamental steps in solving a problem. And we are exposed to this phase already. And this is the phase we have to underline in this course also. How we can adhere strictly to this, and how every solution can be made as per these principles. Now we can see that this part, that is the formation of a sequence of steps, is an important step in computer science. We have seen how this was evolved, and how the word algorithm itself came up, and all these things we have discussed already. These steps are called as algorithms. Now, if you look at the previous question papers, you have a question like define an algorithm. How do you define that? We can say that an algorithm is a well-ordered collection of discrete, effectively computable operations that, when executed, produces a result and halts in a finite amount of time. Let us take all these adjectives of algorithm one by one. First of all, it is a collection of steps or operations. And it is well ordered. What do you mean by well ordered? First should come first. If the order of instructions are altered, there's every chance that the intended result may be different. So first of all, algorithm is a well-ordered operations. Now, what do you mean by discrete? Discrete is a way of telling that the operations or each step is unambiguous, clear-cut steps which cannot be decomposed further. Why we have to make it discrete? Because the program is to be written and ultimately the machine code is to be executed by the machine, a device. We have seen how within a system how the computation goes on. We have a central processing unit. Within central processing unit, we have a control unit and arithmetic logic unit. There is a data bus, and address instructions and data goes together through this bus. There are GPRs, general purpose registers, say accumulators and all these things. Program counter is there, stack pointer is there, base pointer is there. There is a portion of main memory also. Yes, we are still in the art of program methodology, but still we have to worry about these things. Now, how the computation is going on? We know that each instructions will be taken one at a time. We have a program counter for that. Every instructions will be having operands, and some values might be in primary memory. They will have to be fetched to a GPR. Then the addition process will occur, or subtraction will occur, some process will occur. Suppose that we add, say, the value of, say, x and y, what will happen? X is a memory location. So the memory location, value of x will be loaded to accumulator. Value of y will be loaded to, say, a register B. Then we will have an add operation. We will add the contents of A with B and keep the results back in B itself. See, one at a time, one operation is being done by the machine internally, but at a lightning speed. So our instructions also should reflect this kind of fetch and execute cycle. That is why the importance of discrete and unambiguous steps. If you tell me, Halim, go and do that, go and revise, I know what's meant by revision, because you have taught me in my earlier classes how to revise. So just that statement is enough for me. I can do that, inshallah. But what about a machine? As far as a machine is concerned, 1,000 times you tell that each 1,000 time we will have to tell the same set of instructions. You leave AI from this point. I'm talking about the fundamental steps, not about training a machine to be a human. It's another factor which is happening today. We speak about the fundamental things. So since A machine has to do it can only do it in stepwise. Designing the solution also as discrete steps are important. Now, what is meant by effectively computable? This hints at the efficiency of our steps called as algorithm. A program has to be efficient. It should be before efficiency, we'll say that the correctness of the steps will come. You should produce the correct output. If the problem, so first concern is developing a correct sequence, which will produce the exact output required. Once that is arrived, we will measure the efficiency of this program. Efficiency can be measured in terms of space and time. How much primary memory will be occupied by the program while execution, space efficiency. What's the time required to run this program? Time efficiency. Both will be tracked, and effective computable operations will be chosen for the algorithm. Then what happens? Once these operations are given to a machine, it will execute that. After execution, there should be should guarantee a result within a finite amount of time. There should be a halting time. Now we have theory of computations. There you will learn about Turing machines and automatas. You will know the practical importance of all these. Then you will know what kind of a machine is our modern computer. See the mathematical models that were developed by our ancestors, even before the electronic things were developed for that. So make sure that we know what is meant by an algorithm, what's meant by a program in concrete steps. It's a well-ordered collection of discrete, effectively computable operations or steps. And when these operations are handed over to a machine, it should be executed, giving a result within a finite amount of time. That is now, see, you can see that once we spell this sentence, we have even added all the requirements for an algorithm. We say that we have an algorithm, it should have this. Here, we will have a separation of concern. That's how I'll tell you. What do you mean by separation of concern? If you want, you can Google for that. It's not a term related to computer science. It's an interesting term. Please Google for separation of concerns. You will land up in many notions. See, when you say that separation of concerns, we will make our priorities. I will say that, in my humble opinion, the priority in front of us when we do this course is to develop correct solutions. Our solutions are to be correct. We will not worry about efficiency, both space and time here. We have a separate course for that in second semester, inshallah. So our worry is to create correct solutions. Underline that fact. Then flowchart. Algorithms we have seen. Algorithms will be steps that are verbally written. It is said that a picture is worth 1,000 words. So when you can diagrammatically represent a problem, what will happen? What will happen? You will get a better understanding of the problem. And that is being done with the help of a flowchart. So if we are clear about the algorithm, we can say that flowchart is the diagrammatic version of an algorithm. So what are the essential qualities of an algorithm? That should be exactly copied even by the flowchart. It's a method of describing the problem in a different way. There is one more strategy called as pseudocodes. So we have three versions: flowcharts, algorithm, and pseudocode. All these three versions can be used to describe a problem in discrete steps. Pseudocode will be more closer to the programming language that we use to implement. And we can also see that it can have even a direct correspondence. Whereas normally algorithm and flowchart will be even it will not depend upon a programming language in majority of the cases. It will be independent. Once an algorithm or flowchart is written, we can implement this. We can implement that in any programming language. Moving further, what's a flowchart? It's a type of diagram that represents an algorithm, a workflow, or a process. See, don't think that algorithm is only used to represent, no, flowchart is just used to represent a problem in computer science. It is used for several other purposes. One of the use of a flowchart is it can represent diagrammatically an algorithm. And as we know, it's having a lot of shapes like this. Each shape has its own meaning. There will be connectors, and connectors will be given arrowheads. Arrowheads will dictate the flow of execution that is to be done. Flow of execution. A sequence. How the sequence of steps are being done. It is represented by these arrowheads. Now, this first formal flowchart was attributed to Sir John von Neumann. I hope this name is familiar to you. John von Neumann and von Neumann architecture, stored program concept. So all these things you might have learned, say, in your UG days. Now, what are the symbols used in flowcharts? Again, we are familiar with them. See, this oval shape represents a start or end of a process. Machine has to know when to start and when to stop. We know about that. The machine has to know about that. This is a process. What do you mean by a process? How a process will be represented, say, in algorithm and in flowchart. Suppose that we have to add two things. We will say sum equal to a plus b. It's a process. It's a process. If we want to do calculations like this, it will be statements will be written making use of variables and operators. See, we should know. See, when we come with a model of a problem, the model will be having a methodology for solving, and it will require some inputs and outputs. In our case, find the sum of two numbers. We require two inputs. So there has to be two variables represent them, and there has to be a third variable which can hold its sum. We doesn't require that also. If we are not at all worried about storing the result somewhere, we don't require a third variable also. It's another concern. So our process will be represented, say, in these rectangles. Input and output operations. We will be receiving input. Our program will convey some outputs. It can be even alerts. It can be even outputs. Rhombus for that. This is our decision makings and branching part. And what is added here? Here a decision will be made. How a decision will be made? We'll give a relational expression there. That expression will be evaluated to either true or false. Based on the outcome, there can be at least two branches or at least one branch. Then another sequence of steps will be done. This represents a function in simple terms, a predefined process. If you write our own functions, each function will be represented like this. Suppose our flowchart is encompassing several pages. We can put connectors like this so that it is one page, it is finished, then we can continue the same flowchart the next page. These are arrow heads which dictates the flow of a chart. So if you develop a flowchart and you forget to make arrow marks, it's no longer a flowchart. Ambiguity, you are adding ambiguity to a solution and it is not fit for implementation. You can also add comments to your flowchart, and for comments you can make use of this shape. Comments can be added. These are obvious symbols that will come in any textbook or article regarding flowcharts. You can see some additional symbols also in many textbooks. We'll specifically discuss about two of them, which we may use in our problem solving also. One is a hexagon, which is having these 4 values. It represents a loop counter. See, a set of instructions will be repeated based on a counter value, I equal to 0. 0 starts from A. So the counter values start from A. It will be incremented by S until C attains the value of B. The statements will be repeated. So this can be represented using this component of the flowchart. And there is one more loop counter diagram wherein we will make use of a shape like this. Here you can add your initialization part. Here you can update your running variable. So you can say I equal to 0 here. I plus you can put here. Here you can say I less than n. Then you can see that this is false. False is missing. A false should be added. No should be added. Now this you can see this rightly reflects the semantics of, say, a for loop that you might have learned in your C programming days. So this is how we can, these are the nuts and bolts of flowcharts now. See, we spoke about algorithm and suddenly we landed up in flowcharts. So initially we'll take a flowcharts, then we'll see how algorithms can be decided for a problem. So first we'll start creating flowcharts, then we'll revisit all those flowcharts and we'll rewrite them into algorithms. Ultimately, we'll execute them using our knowledge on C programming. That's our intention. What are the conventions for flowcharts? I will tell you some conventions which will have to be strictly observed when you submit your lab works and assignments. At least for this course, we will strictly adhere to this. So please follow this. It's for a uniformity. Only if I tell you that these are required, you will adopt that. So if you fully adopt that, I can give you full credits for that. So there has to be a mechanism to evaluate. See, these are the general conventions. A flowchart will grow from, say, top to bottom or from left to right. There has to be arrowheads to use the flow of information. Suppose that a line is crossing on upon the other. It does not have any logical connection. It's just overlapping. Overlap does not mean any other meaning. It is a flow of control. And any flowchart is very important. Once you write a flowchart, it should have a name. You can give a name as Halim, it's okay. Abdul Halim is good, very good. If you add Abdul Halim PP, I am very happy. But that's not the way of liming a flowchart. If you write a flowchart, say for computing the factorial, you should name it as fact, algorithm fact. That's it. Then you can write the day of your diagram. You can give it a small description that's meant by this title. This flowchart is for this purpose. It takes this many inputs and it produces this many outputs. So there should be a documentation for the flowchart. Then you can draw the flowchart as per these conventions. Once the flowchart is ready, please don't throw it onto the face of the examiner. You make sure that it works perfectly. You will have to make a hand execution method. You will virtually run your algorithm or flowchart, strictly follow the steps specified there. Then at the end, if you get the result good, you can say that my algorithm is correct.